So today we will continue to give an introduction for the typology. It's the first module from your textbook. So last time we mentioned about the, the typology related to the material science. So mainly in the surface treatment, or in other terms, coating, material coating process. Okay? So this is another way you can make a difference from the similar material. So, if one of the material is treated as a surface coating or hardness, making a difference in hardness, so then even you have a similar stock material, such as the cast iron in machine tool, usually we will make some surface treatment from certain member of the frame or structure, so that you will have a different material. Okay? Because if you use a similar material in relative motion, it tends to stick together, so you will have a adhesive wear or adhesive friction. Adhesive friction. So if you can treat one of the material with surface coating, then you can make a difference. Okay? So there are some, I think, some theory or discipline in the material treatment. So first one is surface hardening treatment, or you will have some certain treatment condition for a different temperature, for example, and different coating material. So this is another discipline in material science. Okay? So for physics, for the coating, for the thin layer coating, or thick layer coating. Okay. So last time we mentioned about the chemistry and typology. Normally, it's related to the performance requirement. For instance, if you are using in an extreme high pressure condition or environment, so your lubricant should add some EP extreme pressure additives. Okay? Or if you are using your lubricant in a very high temperature environment, so you should add some specific additives for that. Okay? For instance, you have lubricant used in a combustion engine, so it's in a high temperature condition. Okay? So it requires a different additives. So this performance additives is in a chemical, I mean, in chemistry by nature. So you have a different performance or even some functional requirements of that. Okay? And also we need to consider the compatibility of the lubricant with process fluid or contacting surface. Okay? And some shelf life or stock life. Okay? When you store this lubricant in your warehouse, you need to consider the shelf life for different lubricant and its additives. Okay? And you need to consider different functional requirements. For instance, for a function of temperature or sliding speed. Okay? So we have some optimized composition for your additives or optimized concentration. For instance, the percentage of the additives. Okay? And also, we need to consider the bonding force in atomic scale, okay, from your chemical element. So, for instance, you have metallic van der Waals bond. So, the bonding force from between the atom. Okay. So this area is the chemistry part of the tribology. So from our lectures, I think in the end of this semester, when we mentioned about the lubricant and lubrication, so we will talk about the additives and the composition of the oil lubricant. So it's mainly we will talk about some chemistry in this case. Okay. So you have uh, petro lubricant, you have synthetic lubricant. So there are different topics in this area. So here is the example. You can look at your textbook. This is a famous best top curve for the wear versus wear rate versus the time service time. Okay, so in the beginning, so when we look at the this figures, the horizontal axis is the service time for your components or your mechanical device, and for the vertical axis is the failure rate. Okay, so in the beginning, you have a very high failure rate because all the mechanical components are new, and then they need to have some specific time to run in. Okay, so in the beginning, the failure rate will be high, and gradually as the service time continue, the failure rate will drop into a stable low service rate. So this is the in this area to here, the mechanical device is operate in a normal condition for long service time. Okay. So this is useful life for this mechanical device, and after a certain period of time, usually it's, after the long service life, then you will have a mechanical wear in your component, and then in the end you will have a very high failure rate. The failure rate will increase in the end of the service life. Okay, so this is called the desktop curve for the hypothetical failure rate versus time. So after, usually if you want to have a good operational control for your mechanical device, so at this point you need to change your components or to replace some of the components in order to operate in normal conditions. So if you didn't do any component replacement, so the failure rate will increase. So this is another, yeah, this is another figure in your textbook. So this is a tribal pair. This is one surface with another, one body with another body. So these surfaces are in contact. So in normal conditions, the surface roughness, I mean, the surface of the contacting interface is not absolute flat. So you have roughness between the contacting surface. Okay, if you are adding some lubricant in between this contacting interface, then usually the chemical in your lubricant will have some long chain hair attached on the service on the top of the service. So at this time, with these two bodies in relative motion, so it's sliding on the, on the top of the hair. Okay, so you can have reduced surface, reduce friction of coefficient of coefficient of friction. So this time you will have a smoother motion. You will have less wear on your contacting interface. So, so this is the functionality for your some additives in your lubricant. So to guarantee the chemical attached on the top of the surface. So we mentioned about you can have a reduced coefficient of friction to 10 to minus 2 or 10 to minus 3 to the original value. So if you have just add lubricant, so the coefficient of friction can be reduced 10 to minus 2 to 10 to minus 3. So this is the easiest way you can reduce your coefficient of friction, so by adding some lubricant between the contacting interface. Okay. And how you design the chemical attached on the top of the surface. For example, to form a flexible hair. This is another story for the additives and the chemicals of the lubricant. So we were mentioned in the lubrication part of the lecture. So this is an overview for the introduction for the multidiscipline for the tribology. So, so this is a bit exaggerate service for two, contacting service. So you have a very high tip on top of the service. So this is called the fallacy. So this is extreme high point of the service. It's called the fallacy. So it's a bit exaggerate，就是有点夸张哦。So for instance, we have two surfaces in contact, and you have a relative motion. Okay, this is the most undesirable surface you ever had. Okay, so Actually, we can look at this uh, slide. So you have a one, body two. In contact, you have a loading on top of the body one, and you have a relative motion between one and two, body one and body two. So then, if you have a relative motion, then you will have some your loading on top of body one will induce some stresses. So if you have a relative motion, for instance, like this example here, if they are in contact, so this and this, there will be, if you have a relative motion, usually you will have a stress to break down these stabilities. So that's why we have this one, the breakage, uh, breakage or the elastic bending for your surface stability. Okay, and probably you have a plastic deformation. Deformation may be related to, here we can have a look. So the stability was, the high tip of the stability was broken due to the plastic deformation. Okay? So, so it's due to the plastic deformation. So usually it happens on the softer material for those two bodies. So it is important. You need to know which of the material is of a softer, material, or you have a smaller hardness. Okay, so usually the softer material will be the asperity of the softer material will be broken down. Okay, due to the plastic deformation. So then we will have some. We need to know the surface roughness for each of the contacting surface. So, for instance, we have a different definition for the surface roughness. Okay, we have yeah, we have an average soft surface roughness. So this is the average one. So we measure with a different time period or different distance. Then we measure the high point of the surface, and you have a different number from Z1 to Z2. And in total, we have from a distance of L, you have measured n times for the difference. For the average is you use this formula to get a absolute value average, okay, for your service. So this is one of the notation we use called the RA, surface roughness. It's the average one. So, and also we have another notation for that. It's called the Roomy square. Okay, we take the high point of the disparity to measure the number V1 with the square, and total we have a summation of the n points divided by n, and with the Roomy square. It's called the Roomy square roughness. Okay. So usually we need to look at this one, Roomy square roughness. So we have some comparison for that, for good service or bad service. So it is important to have a understanding for the Roomy square roughness for this one. So with the similar average surface roughness, but to compare the Roomy square roughness, so this one is smaller and this one is bigger. So in this case, you have a dramatic change for the asperity height. Okay. You have a relative smaller change in the asperity height. Okay. And then we have one image from that. This is a microscopic image for the surface. Okay, so you have average surface roughness and Roomy square surface roughness. Okay. So both these two values are smaller than this one. So in that case, you have a better service compared to this one. You have a dramatic change from the high point and the asperity and the body. Okay. 所以这个的话就会有比较大的山峰跟山谷，所以它的变化会比较大，不是这么平均。So in the end, we have yeah, this is the lambda value. It's called the specific film thickness in your stripe back curve. You have a stripe back curve. Wait, I think I have a slide from that. Yeah, this is stripe back curve. This is important when you consider different lubrication regime. You have a boundary lubrication in the in blue color, and you have mixed lubrication in red color, and then you have electro-hydrodynamic lubrication or full film lubrication in yellow color. Okay? So it all depends on the this specific film thickness. So this is the This is a measurement between this, the thickness of the film thickness between these two contacting surfaces. Okay. So it's a measure to know how thick is the specific film thickness for your lubricant, especially for the oil lubricant. 这个我们后面会讲到，就是那个 Strybeck 的曲线，就是定义不同的润滑的原理哦。那个比油墨厚度，因为这个是无因次的式子。So this is a dimensionless parameter. So this is dimensionless. This lambda value is dimensionless. So for instance, you have a film thickness for your lubricant. So this is in millimeter or in micrometer. And this is the lumen square roughness, surface roughness from contacting from body 1. This is the lumen square surface roughness for body 2. So the dimension for the film thickness is in length, maybe micrometer. So this surface roughness is a micrometer. So when you divide these two, it's dimensionless parameter. So this is a dimensionless film thickness parameter. So we call it specific film thickness. So 这个是无因式的式子，上面那个油墨厚度是长度的单位，下面那个表面粗糙度，第一个物体的表面粗糙度，第二个表面物体的粗糙度，加起来开根号，平方加起来开根号。所以这个其实是一个油墨厚度相对于表面粗糙度的比值，所以叫比油墨厚度。它的厚度越高，就表示我两个物体的越分开。那厚度越小，就表示越接近。接近的话，刚刚我们看到有一些尖点，所以其实会接触。So this lambda value is a measurement from the distance between body 1 and body 2, so two contacting surfaces. Okay. So if you have a smaller lambda value, that means part of the surface asperity will be in contact. Okay. So maybe the percentage of contacting asperity is more than 50%. And for mixed lubrication, still you have some high asperity of two surfaces will be in contact. So maybe the contacting area is less than 30%. So if you have a hydrodynamic lubrication, if you have a lambda value greater than certain number, which means that you have a very thick lubricant. So the two contacting surfaces will not have any physical contact. Okay. So in our textbook, we divide it into 4 different categories. Actually, these two, hydrodynamic lubrication or electrohydrodynamic lubrication, some of the textbooks they mix together. So it's only, this curve only, the lubrication regime are classified only into 3 categories. And for this one, we have 4 different categories. So it's a measurement for the film thickness, but it's a dimensionless parameter. So we're using lambda to do so. And then we will have some different theory to calculate the coefficient of friction. So this one is boundary lubrication. Second one is mixed lubrication. And the third one uh, is called the electrohydrodynamic lubrication. In this case, we have four different categories. So we have, wait, you can look at the textbook. Maybe it's better to have better view for that. So this is the wear rate versus the load divided by temperature. So to distinguish it by color, so the red one is boundary lubrication, and the mixed lubrication is the blue one. So this is it's the wrong color. So this mixed lubrication. So hydrodynamic lubrication is the green color. So because for the boundary lubrication, you have a very small lambda value, so most of the parts, I mean the surface are in contact. Therefore, the coefficient of friction is high, so you have higher wear rate. Okay, and for the mixed lubrication, you have maybe 30 to 40% of the surface are still in contact, so you have a medium wear rate. For hydrodynamic lubrication, you have a very thick lubricant thickness. Therefore, you will have no physical contact, so you have a very low wear rate in this case. Yeah. So most of the textbook they are classified into three different lubrication regimes: so boundary lubrication, mixed lubrication, hydrodynamic. Although some of the name will be different, I mean, because we have so many material in contact. Okay. By doing some experiment for different material, you have a different result. So most of the formula or theory from tribology are obtained by experiment. So by doing different material, we have a different result. So everybody got his own opinion. That's why some said you have three different categories. Some said you have four different categories. It doesn't matter. Depends on what kind of material you are talking about. 大部分的那个，大部分模论学的一些理论的基础都是实验得出来。那实验的话，你有太多不同的材料做配对，做出来结果每个人都不太一样，这样条件不一样，所以每个人得出的结论也会不太一样。所以我才会说刚刚我们这边就是把它写成四个、三个或四个，这个只写三个。刚刚我们投影片这个就四个，它把它分成四个不同的区块。那有些把它分成三个，那都没关系，对，主要是看你谈的是哪些的材料，哪些的不同的测试状况。OK， So this is the case for the mixed lubrication. The mixed lubrication, you have some point in contact, some point separate. Also, you have some debris. Okay, we know the asperities will be broken down. So, and then the broken down material will become debris. debris 就是残渣哈，像我们那个飞机失事或船失事，我们都要到海里面去捞残渣，那个就叫 debris。这个是我们的尖点的部分，就是我们前面那个尖点。So here we have some example for the interdisciplinary approach. So under the boundary lubrication condition, this may involve the material science, solid mechanics, and chemistry. So under the mixed lubrication conditions, you have also four disciplines. Under the hydrodynamic lubrication, only the fluid mechanics. And under the electrohydrodynamic lubrication, solid fluid mechanics will be involved. So for the specific film thickness, this one, if the lambda value is big enough, so it separates the two contacting surfaces without any physical contact. And this, in this case, we call it aerostatic or hydrostatic lubrication. Okay. So this is where we always talk about the air bearing or hydrodynamic bearing in machine tools. So, so for the next semester, I have a course just to discuss the hydrodynamic or hydrostatic and aerostatic bearing in machine tool. Okay. And for the aerodynamic or hydrodynamic, it's not, I mean, it's rarely applied in the mechanical application. So usually the hydrostatic and aerostatic bearings, because they are separate, the film thickness is thick enough, so without any physical contact, so you have extreme low coefficient of friction. Okay. For hydrostatic or aerostatic bearing, the typical coefficient of friction is 10 to minus 4 to 10 to minus 6. So typical value is that's the coefficient of friction is very small for the hydrostatic or aerostatic bearing. For the air bearing, it's no physical contact. So and here we talk about the economic benefits. So because you have lower friction, low wear, so you have extend service life, so it saves money. Okay, so the saving will be obtained by reducing energy loss due to friction losses due to breakdown, or reducing the depreciation of the machinery. So there are some examples. I mean, most frequently mentioned the component necessary for the tribological study is the gear, combustion engine. So turbo machinery gears can follow a bearing or seal or clutch. You know, these mechanical components are specifically necessary for tribological study. So the main purpose is was meant to reduce the wear and friction to enhance the service life or extend the service life. Okay, so by doing so, you can save a lot of money. So we have some example in this. So this is also, I mean, one case that needed the study of topological research. It's a magnetic disk from personal computer. Okay, so you have a reading head. Uh, this is a reading head. So in the disk drive, okay, and the second one is the study of the lubrication in combustion engine between the piston ring and the engine cylinder. So usually this is a piston, this is the engine cylinder. So you have a combustion oil and air mixer here, and the piston ring. There are some friction between the piston and the cylinder. So we need to inject the lubricant oil into the inner cylinders. So this is the yellow one is the injected lubricant in the engine. Okay. So here we have a statistic. Approximately 15% of the energy is lost through friction due to the motion of the piston, valve train, and bearing. Okay, so this included the friction between the piston and the cylinder, and also the valve, and also some bearing. Okay, in total, 15%. So this is one of the case, the friction between the piston ring and the cylinder of the combustion engine. And in this case, for the lubricant used in the engine piston ring, it's necessary the lubricant need to add some high temperature additive, okay? Because the inside the engine, the temperature is more than 300 degrees Celsius, so it is necessary you add some temperature resistance digit in your lubricant. Okay, we will mention this about maybe I think in 2 months. So the next one is the valve system. So this is the exhaust valve for the engine. Uh, it's a cam follower system. So this is a cam system. This is a follower, and this is a release valve here. Okay. So there are some friction between this cam follower and this contacting surfaces. Okay. And also we have another example for the iron or steel industry. The bearing in heavy machinery. Okay, so the replacement of the bearing will cost a lot of money annually. So here we have also an estimation. So a rough estimation indicates that 10% of the bearing life can be improved with better lubricant or better lubricant additives or even some proper installation for the bearings. So you can improve the 10% of the bearing service life. So you can save a lot of money for that. So this is the initiation of the tribology in 1966 because of the after the industrial revolution in United Kingdom. So they have some problem for the mechanical failure due to the topological problem. So at that time, so so this is the beginning of the topology. Okay. So we will start to talk about the main topic in tribology. So we will begin with the friction. Okay. So when you are wet in the floor, so you have some lubricant between the floor surface and your surface of your shoes. So it's a reduced friction situation. So we have already give you a brief introduction from the Tribology 101, the PowerPoint from Brooker. Okay. So we know the friction is a system property. So you cannot say the one of the material you have a coefficient of friction. You need to give a clear explanation for the counterpart. So in this case, you see this is a typical value for the coefficient of friction for metals sliding on the self, which means this is two same material sliding. So for instance, so this is aluminum on aluminum. So you have a coefficient of friction 1.5. Couple on couple 1.5. And couple on couple, then we have oxide layer. So because most of the metal are, I mean, you have oxide layer. Okay. The bulk material of the metal will react with the humidity in the air together with the chemical reaction with the oxygen. So you will have oxidation. So in that case, most of the material, metal material, you have an oxide layer on top of the surface. 大部分的金属的材料，空气中有潮湿、有氧气，所以它基本上就是会生锈，会有氧化层在上面。所以 oxide film 就是氧化层。So if you have an oxide layer on top of the couples, so you slide on another oxide layer of couple. So it's like a film of a lubricant in between. So you have a reduced coefficient of friction. So you have this is a specific indicator. You have an oxide layer. Okay. So you have another coefficient of friction, gold on gold, so it's 2.5. Iron on iron, 1.2. Platinum on platinum, 3. Silver on silver, 1.5. And you have a steel, the mild steel. Okay. We have a different composition of the copper, no, carbon in the steel. So this is a mild steel, 中碳钢. So you have a coefficient of friction 0.8. So you have a steel. This is a tool steel. Then you will have a coefficient of friction 0.4. Okay. So for most of the case, if you have a two, this is exactly this I mentioned here. Okay. If you have a similar material, you will have a adhesive friction. Adhesive friction 就是叫粘着摩擦，两个相似的材料它其实会粘在一起，粘在一起就是不容易分开。If you have an adhesive friction, which means they stick together, so the coefficient of friction usually is high. So bigger than 1.0 in most of the case. So even you have a similar material with the steel, but you have a mild steel, you have a tool steel. The composition of carbon steel is different. 含碳量不一样, so you have a different coefficient of friction. And also coefficient of friction depends on the environment. One we didn't mention about is the temperature and the humidity. It's important. I mean, the coefficient of friction will vary depending on the humidity and temperature. 其实我们是没有在讨论这一块。摩擦系数其实会跟湿度跟温度有关系。If you are doing the experiment in summertime and in the wintertime, you will see the difference. The measurement of the coefficient of friction during the summertime and the wintertime they are different. Okay. So always you need to mention about the system property. I mean, this is the aluminum on aluminum, so metal sliding on themselves. Okay. So this is another chart, 2.1, from figure 2.1. So the coefficient of friction for various metals, because we are only focused on the engineering tribology. So metal is one of the material most frequently used in engineering application. So we look at this table. This is the coefficient of friction. You have on the bottom line is 0, 0.1, 1, more than 1, maybe 2. Okay. So you have a different contacting condition. So you need to give a system property. So you have nickel on nickel, gold on gold, platinum on platinum, copper on copper, indium on indium, lead on lead, aluminum on aluminum. So these two, on the top of this table, they are high, more than 1. Okay. 所以这个是镍、金属、白金、铜、阴、铅，这个是铝，再来是银，iron on iron，就是这个铸铁，锡，tin on tin，steel on tin alloy. So below this, you have steel on tin alloy. 钢铁材料在那个锡的合金。Okay. So we have a different material. It's not the same as steel on steel. Steel on lead alloy. Steel on the aluminum bronze. Steel on cast iron. Steel on brass. Steel on bronze. Steel on lead brass. Steel on indium. Okay. When you look at the table, you will see if you are contacting with themselves, the metal contacting themselves, you tend to have a higher coefficient of friction. If you are contacting with a different material, you have smaller coefficient of friction. Okay. This is the reason. For the similar material, the metal contact on themselves, you will have the adhesive friction. So you tend to have a very high coefficient of friction. Okay. If you are contacting with a different material, the adhesive friction is not existing. So you have a smaller coefficient of friction. Okay. So in this table, we mentioned only the dry friction. So the contacting condition without any lubricant. Okay. So it's called the dry friction. So without any lubricant. So it's called this is the no. So you see, if you have a par lubricant under dry lubricant condition, the coefficient of friction, dry lubricant or dry friction, the coefficient of friction is between 0.1 to 1 for most of the metal material. Okay? So if you have a thin layer of lubrication, it may reduce the coefficient of friction by 10 times. I think it's more than 10 times, maybe 100 to 1,000 times. Okay? Uh, this is typical. If you are adding, this is more in conservative time, I mean conservative side. 所以你加了润滑剂，至少我的摩擦系数会降为原来的至少是1/10以下，大部分的时候是1%到1/1000。所以这边跟你讲，so coefficient of friction with a partial lubrication, the coefficient of friction will be reduced to the 10 to minus 1 to 10 to minus 2. If your film thickness is thick enough for coefficient of friction for full hydrodynamic lubrication, which means it's very thick lubricant. So the coefficient of friction will be reduced 10 to minus 2 to 10 to minus 3. 所以如果只是部分的润滑，的摩擦系数可能降原来的1/10到1%。如果是全油压润滑，就是油膜厚度非常厚的话，它们是变成1%到1/1000。我们刚刚讲的。So to overcome the friction, adding lubricant is the most effective way. 所以如果是要改善摩擦的话，加润滑剂是一个最有效的一个方式。So we have a kind of material pairs. Okay. So this is so for the horizontal axis you have a different method. The vertical axis another different method. So you have a combination between these pairs. Okay, then you will have some result. Here we have a notation here. Okay, for the black one is low adhesion. Low adhesion. Okay. High adhesion means that they tend to stick together. Okay, low adhesion is not open; they will stick together. 有高的粘着性，就是两个配对起来，就是会粘在一起。粘在一起就是不容易分开，就是它的摩擦系数是非常大，就是粘在一起。低的粘着性就是它不容易粘在一起，就是很容易分开，所以它的摩擦系数就会很小。When you are doing the mechanical design, you need to choose your component material properly. So if one of the fixed is a fixed frame, another one is moving members, then you need to choose the correct material. 所以你在做机械设计，动件跟不动件设计是很重要，你要去选不同的材料，选一样材质或相似材质，它其实会粘在一起，会有比较大的摩擦系数。So this is the figure. We have a more comprehensive table. You look at the book. So this is the heat friction among various materials. Yeah. 所以这个是铟啊，铟点半导体的那个常用的元素铟、铅、锡、钙、镁、锌、铝、银、金、铜、钛、锡、白金、镍、铸铁。这不是，这不是镍，这个才是镍，nickel 才是镍，cobalt 是那个 cobalt 是那个磁铁，铬这个是镍，嗯，这个是钨。So this is a classical result from the static friction and kinetic friction. We all know we have coefficient of friction, static and coefficient of friction, dynamic or kinetic friction. So we have a footnote S, a footnote K. So it's static and kinetic. So this is by experiment you will know. Okay. So at the point number 3, you have the highest coefficient of friction. Is the static coefficient of friction. So above mentioned notation is all the coefficient of friction, static coefficient of friction. Once you overcome the static friction, so the coefficient of friction for kinetic condition it drops. Okay? So once it's in motion, the coefficient of friction, kinetic coefficient of friction drops. So this is obtained by the experiment. Here we have experimental results. Okay. It's also system property. So you have a material combination. So wood on wood, wood on wood in dry condition. Okay. Of course, you see we have at least 3 or 4 or 5 different conditions wood on wood. Okay. The testing results are different. Okay. So for this, we know the coefficient of friction is not just related to the material, it also related to the temperature and humidity. For this moment, we still do not have an exact model for the friction, I mean static friction. Okay. So we have a different wood type. This is the oak 那个橡树，橡树。国外比较多橡树，他们做软木塞，就是酒瓶的软木塞的话，都是用这个橡树做。So we have a different microstructure. We have a different structure for the grain size. So 我们有不同，其实木头的纹理有不同的纹理。这是我的那个木纹，如果是垂直，那这个是平行 parallel，平行我们的那个木头的颗粒，这个是垂直。这个如果是片状平行，这个如果是片状交叉，它会有不一样的摩擦系数。You can also look at the kinetic coefficient of friction. It's smaller, slightly smaller than the static coefficient of friction. So this is a result there by experiment. So we also have some observation. This is observation during the experiment. So for the wood on wood, the coefficient of friction usually greater than 1, and the coefficient of friction depends on the environment, hardness, and the chemical composition. And the third one, very thin and thick lubrication reduce 10 and 100 times respectively. So then we talk about the tribal pair. Okay. You have two bodies in contact in relative motion. So those two bodies are tribal pairs. 通常我们会把这个物件一跟物件二表面接触做相对运动，我们把这一个物件一跟物件二叫做模润对 （tribal pair）。For tribal pair consisting of similar material are having higher tendency of coefficient of friction. This is due to the adhesive friction. If you are in similar material, then you tend to have higher coefficient of friction. So the difference between the static coefficient of friction and the kinetic coefficient of friction may initiate the friction instability. 它可能是会有不稳定的状态。So this is in dry condition. So the above mentioned experimental results, they are tested under the dry friction. Okay, the tribal pair are tested under dry friction without any lubricant. Okay. So this is the first body. This is the second body. These two bodies is called the tribal pair. Okay, and sometimes you will have a third body. Okay, the third body is the debris we mentioned before. So debris you have a relative motion. So the high stability may be cut off. So it becomes the debris. So this debris is the third body. Okay, we have a very famous theory of abrasion. So, so this debris is the third body. So if you consider the abrasion theory, the three bodies is called the three body abrasion. If you consider only the tribal pair, the body one and body two, without the debris, called the two body abrasion. So later on we will discuss this. Okay. So from historical point of view, this is the beginning of the study. It's on the topic of dry friction. We may now start to introduce you some of the famous dry friction theory from history. The first one is from the Da Vinci. Okay, so this is the earliest experiment dating from the 1462. Okay, from the Italian scientist and also artist Da Vinci. So this is the result we copy from his note, okay, from the literature. And friction made by same weights will be of equal resistance at the beginning of movement, although content may be of different breadth or length. Okay, so this means that friction force is independent of the contacting area. Okay, this is the note the comment we made from the understanding of science. From now on, we give the note here. Okay, and the second conclusion is that, or second observation is that the friction produce the double the amount of effort if the weight be double. So, which means that the friction force is proportional to the normal weight. Okay? So this is the first study of dry friction from history. Okay? And the second one is the French scientist. Okay, we take a break. Okay, continue. The second study result is from a French scientist in 1699. So he rediscovered Leonardo's law of friction. So the friction force is independent of content their area. So the friction force is proportional to the normal force. And he also observed the result for most of the materials, the coefficient of friction is equal to the 0.3. Okay, so here the normal force is the gravity of the object mass, okay, multiplied by gravity. Okay, this is the normal force acting on the contacting interface. So if your friction, if your applied force is not in parallel direction of your movement, so you may have an extra normal force on the vertical direction. Okay, so we have two different conditions. We have extra force applied on top of the surface. This is a pulling force on top of the object. Okay. We now know the normal force will change. Okay, so this is a different. This is a new normal force. in this case. This is another case. Of course, this is what we understand for the formula at this moment. So this is you found out in the literature from the document. So for an object sitting on a flat surface, the normal force is just its weight. If a force acting downward on the object, the normal force is greater than the weight. If a force pulling upward on the object, the normal force is less than the weight. And later in 1781, this is another result from Coulomb. So we have three, he had written down three different statements from the observation. The first one is clearly distinguish between the static and kinetic friction. This was obtained by the experiment. Okay, and the second one, the contact at a discrete point. Okay, this is assumed by the Coulomb in the 18th century. So because the top surface is not really flat, so you have stability and volume at this moment. So the contact only in some discrete time at discrete point. Okay, and you have a result. The coefficient of static is greater than the kinetic is because the stability on top surface was moving into the valley of the bottom surface. So in this case, so you have a higher or bigger static coefficient. And the third one is friction due to interlocking of the rough surface. So this is the observation from Coulomb. Okay. So this is, this is more or less true. As we know, the surface roughness of the two surfaces are not absolute flat. So the friction, yes, is happening due to the interlocking of the rough surface. 所以库伦就发现这个，其实摩擦是因为粗糙表面互相锁在一起。那动摩擦的话，其实是因为尖点的部分被打破，其实是因为材料被磨掉，所以它没有那么尖，互锁的状况没有那么严重，所以才会动摩擦系数会降下来。And then we have the force observation. So the friction force is not a function of the contacting area. So and the fifth one is the friction force is not the function of the velocity, the moving velocity in relative motion. Okay. So this theory is more or less the same as the dry friction we understand. So that's why usually we call the Coulomb is the inventor of the theory of dry friction. 所以这个干摩擦的理论其实跟我们现在了解的是差不多。 我们通常都把库伦当作是干摩擦理论的发明者，所以我们常常讲叫做，so we call it the dry friction is called Coulomb friction。所以我们通常把干摩擦叫做库伦摩擦。So we have another different theory. Okay? This is for the theory of molecular attraction. So the friction is due to the molecular attraction between two contacting bodies. 所以我们这边还有一个新的理论，就是我的摩擦力是因为分子之间的吸引力。So the relation between the friction coefficient and elastic property of material are involved. So the first one is the friction force. Okay, then you have Young's modulus involved here. Okay, you have theta one, theta two. Theta one is a material one. Or theta two is a material two. Okay, and you have theta equal to the Young's modulus. Okay, and shear Young's modulus. These two is a combination of these two. Okay. So this is related to the material property. So it gives, this is also experimental result, but it become an empirical formula. 这是从实验结果归纳出来的经验公式。It's easier if you have this analytical formula. So you just substitute the formula, I mean the parameters of Young's modulus and shear Young's modulus into this two equations. You can calculate the coefficient of friction. No, friction force, okay, in this case. So we have some example. This one, we have clean steel material. We have aluminum. We have titanium. Okay, you both have the Young's modulus and shear Young's modulus. So if we are calculating the friction force between the steel and aluminum, so you will get the coefficient of friction. In this case, there's a calculation. We can look at yeah, here. So this one is the COF, but it's not really friction. It's coefficient of friction. So this one is COF, coefficient of friction. By calculation, you can have these two material, two tribal pair, you get the coefficient of friction. These two tribal pair, you get the coefficient of friction. And these two, you get the result by using these two formulas. So due to the molecular attraction between the metals, the co-welding junctions are formed. So if you have a contacting force on top of one body, so when the force applied, you have co-welding junctions between these two contacting abilities. Okay. These are the different theories from the history. Okay. So now we have a better understanding about the dry friction. So here are the scientific explanations about the dry friction. So we have actually we have two sources of friction. So one is from the deformation. The second one is from the adhesion. Okay. So we have first body, second body. We have normal force or normal load applied. Nothing. So we have a relative motion. The friction usually generated by two different sources. One is deformation, another one is adhesion. 主要是两个摩擦的来源是一个变形，一个是粘着拧在一起，一个是产生变形。So the resulting friction force is the sum of two contribution terms. Okay. With a subscript A means the adhesion. With a subscript D with the deformation. So it's FA and FD. So if you have a lubrication between the interface, so if you are lubricated the tribal pair, in that case you can neglect the adhesion. So you rule out the possibility of the adhesion during the two contacting pair. Okay. If you have a smooth surface under light loading condition, so you can neglect the deformation. So this is extreme case. Okay. So this is the asperities from the top surface. So if we assume the bottom surface is the soft material, then the top asperities can have a scratch on the bottom surface. So you can generate some friction force on the softer material. So this is the term of deformation. Okay. So this is the FD, I think, yes. FD. We have two different assumptions for the asperities. One is the conical asperity. Another one is the spherical asperity. Okay. 所以有两个摩擦摩擦力的来源，一个是粘着产生的摩擦力，一个是变形产生的摩擦力。变形主要就是假设上面是比较硬的材料，下面这个面下面这个物体是比较软的材料，上面的尖点就会在下面这边有一些刮痕。如果它做相对运动，就会产生一些变形。那尖点的部分，我们后面会去讨论。尖点有两个假设，一个是锥形的尖点，一个是球形的尖点。就是它尖点的形状是锥形还是球形？当然，它刮除的面积会不一样。And this is the height h is the penetration depth. Okay. So this is the conical angle for the fallacy. This is the contacting radius at the height of h. Okay. 所以这个是穿透的深度。那这个对应的是在这个穿透深度底下，锥形的半径。Because in the end of the day, we still need to calculate the wear rate or wear volume. 通常我们要去考虑那个磨耗量或磨耗的体积的时候，我们就要考虑它的穿透深度啊、半径，那我才知道它移动一定的距离之后刮除的磨耗量、材料的磨耗体积。So this is important. We know the dimension for the penetration depth and also the radius of the conical radius at each step. Okay, so that we can calculate the wear rate and the wear volume for the material removed. So, so now we start to give you some theory about, introduce you some theory about the friction. The first theory is adhesion. Why, if you have a similar material, triple pair of a similar material, you will have adhesion. It's called the adhesive friction. So first we discuss about the adhesion. So we have an example for this one. So maybe we look at the textbook, you can see more clear. So this is a typical, this is standard shot with carbon graphite seal. You have you place your seal into this place, and after serve a period of time, you will see some of the carbon or graphite sticking on the shaft surface. This is a typical phenomenon of the adhesion. Okay? So, by experiment, you can do that. It's called the co-welding. So if you use a steel pin to contact with indium, indium is the material. So if you're using the steel pin, of course you need to place some loading on top of it. So it has So the steel contact or indent in the Indian to a certain extent, if you remove, then you will see some part of the material Indian will attach to the tip of the steel pin. Okay? So it's called a cold weld. It's an effect of a cold welding. So the material of Indian was attached to the steel pin. Okay? So this is a phenomenon of the adhesion. So these two are the example of the adhesion. One material stick to another material. It depends on the hardness. Okay, hardness is the key to decide which material attach to which one. So the softer material will be removed and attached to the harder material. Okay, so in this case, graphite is a softer material. So the graphite will attach to the steel. On top of that, the Indian is a softer material. In terms of the honey, so to compare these two materials, honey, when you place this pin with some loading, then you will see the softer material will attach to the harder material. So this is a phenomenon for the adhesion. So from this observation or from the experiment, you will have some conclusion for this theory. So starting from now on, we will have a lot of different theories from different experiments and different observations. So it may give you some empirical formula. Okay. So what is the empirical formula? Is that the formula was obtained by experiment. Okay. From the statistic data of the experiment, you can give you empirical formula. 所以我们很多这个摩瑞学的其实都是经验公式，它经验公式其实是从那个实验结果来的，实验结果来它去近似成一个公式。Okay, with this formula, it's easier you can describe the characteristic or to estimate or predict the performance. So these are the empirical formula. Okay, they are deduced from the experiment. Okay? 其实是从实验数据去做回归方程近似出来的公式。So here are the theory of the adhesive friction. Okay? So you have a tribal pair, you have a loading on top of it, so you have a relative motion, so you have a friction force. So these are the asperities. So the contact only happens in some specific areas. Okay, so the contacting is here, and then you will find out some of the material are removed from softer material to attach to the harder material. Okay, so here are some of the description for this the adhesive friction. So two surfaces are pressed together under load W. The material deforms until the area of contact. So in the formula, A is the contacting area. So it's sufficient to support the load of W. So the contacting area can be decided by this formula. The normal loading force W divided by the hardness. So this H is the hardness of this of the soft material from the tribal pair. Okay? So it's a soft material beside the contacting area. 接触面积的大小是比较软材料的硬度来做决定，它是它的垂直方向的负载除上软材料的硬度。To move the surface sideways, so you have a relative motion. So we must overcome the shear strength of the junction with the force of SA. Okay? So it's a co-welding. You have a adhesive connection from this asperity junction. So we can calculate the adhesive force. The, the sub node here is the adhesive. Okay. This was equal to the contacting area multiplied by the shear strength of the softer material. So this S is the shear strength of softer material. So in that case, we know the coefficient of friction is equal to the friction force divided by the normal force, W. Okay, so you substitute this one into here, and you replace the W equal to the A multiplied by 100. So you will have a result. The coefficient of friction in adhesive is equal to the shear strength of softer material divided by the hardness of softer material. So, so this is a famous formula for the adhesive friction. Okay. So we have a note here. The observation is that the shear strength S and the hardness H of soft material decide the value of coefficient of friction. So this means whatever properties of the other harder pairing material, the coefficient of friction would not change. Okay, so for the adhesive friction, the coefficient of friction was purely decided by the softer material. Okay? So when you are doing the mechanical design, it's the softer material, the important one. It's not the hard material. Okay. Any question about it? So we know about if you if the triple pair are similar material, the main contribution for the friction, the adhesive friction. You can look back on the tables. If the material is sliding on themselves, so the main contribution for the friction force is the adhesive friction. So we can calculate these properties by using this formula, the theory of the adhesive friction. Okay, so here we have some statement in your textbook or in your material, course material. For most of the untreated material, the hardness can be equal to 3 times of the yield stress of your material. And the shear strength is equal to the yield stress divided by 1.73 to 1. Okay, you can using this formula to calculate. So here what I wrote down here specifically, the sum node for this one is adhesive. So, okay, using the formula strength divided by the hardness. Okay, so you can expect most of the value coefficient of friction equal to zero point 0.2, 0.2. Look at the what we have some historical documents here. No, not here. Maybe. The theory is unable to estimate the different coefficient of friction for steel on India, steel on lead alloy. Okay? So we have a different theory should be explored for the friction theory. Okay, so as we mentioned, there are two friction sources. One is from adhesion, the other one is from deformation. Okay, so so now we need to explore some of the or give you some explanation for the friction due to the deformation. So we have some statement here. So So the first one is that the contact between the tribal pair only occurs at discrete points. So 在我们的在我们的模论对的接触里面，所以它的接触在一些离散的点，其实就是两个接触表面的尖点的部分会接触，最先接触。So the slope of the asperity will govern the friction force，就是我们的尖点的斜度，其实会主导我们的摩擦力的大小。And the third one is harder asperities will penetrate into the softer surface，就是硬度比较硬的材料会穿透到比较软的材料表面。So now we are going to find out the empirical formula for the friction force due to the deformation. Okay. So we assume in the first place the, the asperity is a conical asperity. Okay. So for the hard material in contact with the flat soft material, okay, the vertical projection area of contact, we assume we have n contacting points, and each of them you have a contacting area, this one. So this is the the surface area from the conical asperity. So it's 1/2 of pi r squared. We have n contacting points. This is the total contacting area. Okay. And for the for the normal force W equal to the contacting area multiplied by the softer harness of softer material. So contacting area A multiplied by the harness of the softer material. Here we have this. Okay, this friction force can be using this one. This one. This is the deformation. This is the friction force for the deformation. Friction force is multiplied by the contacting area. So this is not so difficult. You can obtain this conditional friction for the deformation. For the conical shape of the spaghetti.